Hey guys, welcome back. We're still continuing day 10. We're going to talk about now mechanisms. Reaction mechanisms. And this would be the sequence, or the series, of individual chemical steps that is the sequence of bond breaking and bond making. Each step is an elementary step. Each step is an elementary step, and it's characterized by its molecularity. And that molecularity would be the number of molecules involved in the step. The molecularity can be characterized in three ways that we're going to talk about: unimolecular, bimolecular, and termomolecular. And you guys can probably figure this out, but unimolecular involves a single molecule, such as like decomposition. Bimolecular would be a collision of two molecules. And termomolecular is the simultaneous collision of three molecules, which is somewhat rare. Right? That's a harder thing to do. Does it happen? Yes, but it's harder. So when we talk about the rate of a reaction, all right, the rate law can be written based upon the stoichiometry of an elementary step. So not the overall reaction, but the elementary step. And the slowest step is the rate determining step. So the slowest step is the rate determining step. So there's a picture here from the textbook where we have 3 lanes of traffic go into 1. And that really slows down traffic, especially if there's any appreciable amount of cars on the road. I personally like the analogy of running a relay race around a track. So if we had 4 people going to run 100 meters, that would be 1 lap around the track. If I'm on that team with 3 faster guys, I would be the slowest person on that team, which I would be the rate limiting section, right? Because our time would be totally dependent on me. They're so much faster. I'm the problem if we want to get faster. So that would, just like here, and then back to the traffic, once this construction done is complete, then the traffic goes much faster. But right now, this is the rate limiting step. It's a slower step, and that's the step we can measure. So when we have these reactions, we can measure the slow step. A lot of times, the faster steps we can't measure. Sometimes we can cool them down enough and make them freeze them or whatnot and get pictures of them. But most of the time, the slow step is the only one we can measure. So let's do an example here. So I'm going to have hydrogen gas, H2, plus 2 ICl, iodine monochloride, going to HCl plus I2. Right, so we're going to propose a 2-step mechanism. Step 1 in green would be H2 plus ICl, has a K, rate constant K for that step, K1, going to HI plus HCl. And we're going to say that's slow because we'll tell you why that's slow in a second. Step 2, we're going to suggest that HI plus ICl with K2 goes to HCl plus I2. And we're going to say that's fast. If I add up the green and the purple, right, step 1 and step 2, I should get the blue reaction, which I do. Now there's something that I want to point out here, and that is HI. What is HI? HI, all right, hydrogen iodide, is not in my reaction. It is an intermediate. Which means it's produced in reaction, right? It's produced in a reaction in an early step, right? And then consumed in reaction in a later step. So intermediates are produced and consumed. The rate law comes from the slow step is equal to H2, well, I missed K. Don't miss K. K, and it's K1, but we just say K because it's K1, but we're just going to use K because we can't measure K2. Concentration at H2 ICl. So the rate, we just call it rate constant K because K2 is so much faster we don't even notice it. H2 ICl. So the rate law has to, so again, which one's experiment? This is very important. The rate law is from experiment. All right, we did a method of initial rates, came up with the rate law. So our proposed mechanism has to be constant or consistent with the rate law. If it's not consistent with the rate law, our mechanism is not valid. Right? How did you build that? Didn't work, right? Can't do it. So if this rate law is not consistent with the slow step of the mechanism, we have a problem. So make sure your mechanism is there. Now, here's a energy diagram of this, and how do we tell slow or not? So here's what we talk about. We have a two-step process here. Okay, now this is just a figure from the book, but it'll apply. We got step 1 and step 2. And if you look, you got EA1 and EA2. In this case, the activation energy is greater for 1 than 2. Right, so think of it as a roller coaster. Once you get to the top hill, you're going to go down. If EA2 was bigger than EA1, EA2 would be the rate determining step. So EA1, the first step, is rate limiting because it's got higher activation energy. Delta H is still delta H, but we still have to do with the activation energy has to be met. So let's do an example from the book, number 78. Consider this two-step mechanism for a reaction. So it says nitrogen dioxide plus chlorine gas goes to ClNO2. We don't learn how to name those. And chlorine atom, and say that's slow. NO2 plus Cl goes to ClNO2 again. That's fast. What's the overall reaction? So for A, we add up. So it looks I had to add up step 1 and step 2. So if I add up, I get 2 NO2 gas plus, it looks like, now this is important. You see how Cl cancels if I add them up? Cl2 going to 2ClNO2. So that's the overall reaction. The intermediate for B, Cl gas, is my intermediate because it's produced and then consumed. And finally, the rate law. C, the rate law, comes from the slow step. All right, C, slow step right here. So for C, the rate law would be rate equals, now it's K1, but you just have to write K. You don't have to write K1. If you do, sure, you can. That'd be fine. Concentration NO2, concentration of Cl2. And that is number 78. Let's look at number 76 now. Consider the overall reaction which experimentally observed to be second order in X and first order in Y. So that tells us that the rate K, second order in X, and first order in Y. Okay, that's experimentally observed. Does the reaction occur in a single step where X and Y collide? Well, that would be yes or no, right? And if that's true, the slow step would be X plus Y going to XY. So the rate law would be rate equals K times concentration of X times concentration of Y. And since this rate law is not what we observe, the answer would be no. Right? It says no, the reaction cannot occur in a single step in which X, Y collide because the rate law would be rate equals K times concentration X times concentration Y. This is not consistent with the stated rate law of rate equals K concentration of X squared Y. The next then, is this two-step mechanism valid? Well, what is going on here? I have a fast reaction, so this is the next chapter we do, is equilibrium. All right, if you haven't covered equilibrium yet, equilibrium means reactions go forward and backwards. And I think we've mentioned it several times, like, with dynamic equilibrium and vapor pressure and whatnot. So this 2x going to x2, k1, k negative, or k2. They put it k2. Sometimes you'll see it as k negative 1. So let's try this. Is this valid? How do we validate this mechanism? So using the fast equilibrium in the first step, right, the rate is K1 times the concentration of X squared. Nice. Also, you can use, I think there's a typo here. There's a typo. Let's call this K2. So we're going to call this K3. So we got K1, K2, K3. That'll work out better. So right now, from the slow step, the rate is equal to K3 times the concentration of X2 times concentration of Y. Well, why isn't that the rate law? Well, because here's why. We can't control the concentration of X2. It's a product in the first step. I have to be able to, so only thing that can be in here in this rate law are things we can control. The concentration of the reactants. If there's a catalyst, which we haven't talked about yet, we're going to talk about catalyst real soon. If there's a catalyst can go here too. Intermediates cannot be here. All right? X2 would be an intermediate. It cannot be in the rate law. So what do we do? Well, we see that there's also a rate going backwards of K2 times the concentration at X2. Now, the thing about equilibrium, this rate equals that rate. So we're going to look at the blue rate will equal my purple rate. How fun is that? So that means K1 times concentration at X squared equals K2 times concentration at X2. Now I need to substitute in for X2. So what do? We divide both sides by K2. So that means in purple here I have the concentration of X2 equal to K1 times concentration of X squared all over K2. Fun. So now we can substitute this right there. So my rate will equal K3 times K1 all over K2 times the concentration of X squared times the concentration of Y. Rewriting this one more time, rate equals, this is going to just be K now, the rate constant, times the concentration of X squared times Y. So mathematically, this can work. So this is consistent with the experimentally derived rate law. So the answer is yes. Yes, it is. Right? Because I can do some algebra and do this. You know, some people actually do like doing this a lot, and some people don't. And that's okay if you do. It's okay if you don't. But this is how the process is done. And so that's about as complicated as it gets in Chem 2.